Thank you. Firstly, thanks to the organizers for inviting me here. So 3 of you here. So actually the topic of what I do is not quite related to anything that's happening in the workshop. So I don't know if it is particularly appropriate, but yes, anyway, so this I see that some others are also talking on random matrices, so I'm not the only inappropriate person, so it's okay. So what I'll talk about is limiting spectral distributions of certain structured random matrices. So everything that I say is joint work with Anish Malik. He was a postdoc in ICTS till a few months ago, 2 months ago, and currently he is in Chile doing another postdoc. So what is the question? So let me start by telling you. So the main objects in this lecture, there are 2 things. One is Toeplitz matrix. So what is a Toeplitz matrix? It is a matrix which looks like this. The entries are the same along all the diagonals. So that's what a Toeplitz matrix is. So you have x naught, all the diagonal entries are the same, and the next diagonal entries are also the same, etc. up to x n minus 1. And so that's what Toeplitz is. So there will be other things. For me, in this talk, we'll only consider symmetric, real symmetric Toeplitz matrices. So I'll put the same x1 here also. So this is what a Toeplitz matrix looks like. And the other object is the Hankel matrix. What is a Hankel matrix? It has, the entries are constant along these anti-diagonals. Okay, so you have some entry x naught here. If this is x1, then so is this one. And if this is x2, this will be x2, x2, and so on. It goes on up to xn minus 1. So on this diagonal, they will all be the same. And then some xn and goes on up to x2n minus 1. So in Toeplitz matrix, if you know the top row, for symmetric, everything is symmetric. So Hankel is always symmetric by anyway. So, so if you know the first row, you know the whole matrix. Here you need to know this and this, then you know the rest of the matrix. Okay, so what is it? So in our case, we are considering random matrices with this structure. So in the entire talk, you can take xk to be IID normal 0, 1. IID standard Gaussian entries. So the object of study is this. So what is it that one wants to know about it? It is about the eigenvalues of this random matrix. In random matrix, we study mainly the spectrum, eigenvalues, eigenvectors. Very little is known about eigenvectors. So this, here, if you plot the histogram of eigenvalues, so as the matrix becomes larger and with these entries, the eigenvalues also become larger and larger. It turns out that the correct scaling is to scale down the eigenvalues by square root of n. Okay, so if you scale down the eigenvalues by square root of n, this is a real symmetric matrix. So they are all real. The histogram roughly looks like this, from about -3 to 3. That's what you see when you, if you just, it's very simple to simulate this and you see this picture. For hn over square root of n, so you see a picture which is like this. This goes from about -2.5 to 2.5. Okay, so that's what we see numerically. And so it was, I think in 99 or 2000, Zhidong Bai was the one who raised the question of studying this type of random matrices. Till then, many other types of random matrices were studied, which I'll not talk about. It's not relevant to the matter at hand. But so his question was, what can we say about the eigenvalues of these kinds of random matrices? Okay, so in particular, the entire talk will be about making this precise. Many results are known. First, I'll recall what is known and then say what we have done. Okay. So what was known? So after Bai's paper, so in a paper in 2003, maybe publication was 2006 or something. So Byc-Dembo-Jiang Dembo and Tiefenjiang. They proved that this limiting histograms exist. Okay, so for that, let me make precise how do we study this? If we want to say that when n is large, the histogram looks close to this. So what is the way to make that precise? The way to make that precise, it's a standard thing that we do in random matrix theory. We consider the empirical spectral distribution. Okay, so let me write here. Which one? Xk's are ID normal 0, 1.
Yeah, the X's are ID normal 0, 1. So Tn can be both positive and negative.
Tn is a matrix. So sorry, Hn, I did not write what is, this is Hn. Yeah. Tn is a matrix. These are the eigenvalues, histogram of eigenvalues of this matrix and of that matrix.
So this is bimodal and that's unimodal.
That's what it looks like. It has not been proved so far. So it is very clear in the pictures, it is not yet proved. So what one studies is to make this precise for the shape of the histogram, one looks at the empirical spectral distribution, which is you look at the eigenvalues as a probability measure by putting, so let lambda 1, lambda n be the eigenvalues of Tn over root n or Hn over square root n. So, and then you form the probability measure which puts mass 1 over n at each of the eigenvalues. So that's how you look at the histogram of eigenvalues, the empirical spectral distribution. So which I'll just write ESD. And you can also look at a bit simpler than that. That is a random probability measure because Tn is random. So this spectral distribution itself, eigenvalues are random. So this is a random probability measure. But if you can also look at Ln bar, which is the expected Ln. That's if you take a convex combination of probability measures, it's another one. So expectation, that's another one. This is the expected DSD. This is just a sequence of measures. Okay, so instead of random probability measures, it's a sequence of measures. What they showed was that in both cases, Ln and Ln bar, they converge as n goes to infinity to certain measures, mu t or mu h, let me call it. So these are non-random probability measures on the real line. Okay, so they showed this that these things have a limiting measure which is not random. Okay, but what was okay? So anyway, so that's the result. But how did they do it? It's a well-known technique in random matrix theory, and it is very useful in probability when talking about convergence of measures. They did it by what is called the method of moments. So I'll just very quickly tell you what is the method of moments. Method of moments is if you want to say a sequence of measures converges to another measure, you just try to show that the moments converge to, so you take the moments of this, let's say Ln bar. Okay, so if you take the moments of Ln bar, so let's say x to the p Ln bar of x. That is the pth moment of the expected empirical spectral distribution. So the point is our assumptions are on the entries of a matrix and we are trying to say something about eigenvalues which are a complicated function of that. So you have to have some way of linking eigenvalues and the entries, and that is, so by the way, this just means what is this? This is just 1 over n summation lambda k to the power p, right? By definition, that's the moment, pth moment of that. But the thing that links the eigenvalues and the entries of a matrix is the trace formula. Sorry, there is an expectation here. Because these lambda k's are random, thank you. So this is just the expectation 1 over n trace of Tn over square root n, let's say, to the power p. So same applies to the Hankel case. Let me just write it in the Toeplitz case. So this is, now you can write this, you can expand this in terms of the entries of the matrix. Maybe not. Expectation Ti1, I2, Tip, I1. So you have to do this. So in principle, it is doable because you have the handle on these entries. They are normals, but of course, many of them can be same. That's what is the point. You have to figure out which ones contribute, which ones don't contribute. Some combinatorics is involved. So in the end, after much work, they show that this converges to some number, alpha p. Okay, so in the Toeplitz case, it will, let's say, in the Toeplitz case, it converges to some alpha p. This alpha p is an extremely complicated quantity. There is no expression for it. There is an expression for it. To calculate, let us say, the pth, well, the odd ones are easy, they are all 0. The even one, the 2pth moment, to calculate alpha sub 2p, it is written as a sum of something like about p factorial integrals. Each of the integrals is of over the 0, 1 to some power p or so. So it is a very complicated expression. We don't have a handle on it.
So p's are integers.
Yeah, p's are integers. Yes.
And then your type, right?
No. Once this happens, so now you expect that, well, whatever is a measure, if there is a unique measure with these moments, that will be the limiting spectral distribution. So all you need to know is that although you don't have a good handle on what exactly it is, if you have a reasonable assumption of control on the growth of them, then there are theorems which assert that they are the unique moments of a unique probability measure, and that measure is mu sub t. That's all. It's not very explicit what is mu sub t. Okay. So same with the Hankel case. Yes. This one. That's the definition of Ln bar. Ln bar is the expected empirical spectral distribution. The pth moment of Ln is just 1 over n summation lambda k to the power p. So Ln bar is just the expectation of that. It just means any functional expectation under this is the, well, integral over this is the expectation of the integral over this. That's what it means. It's, yeah, well, you have to do an additional improbability thing. But my point is, they have already shown this, that this mu t exists. But the problem is, what are the properties of mu t? Moments tell you some information about measures, but not everything. For example, for moments, it was easy to see that it goes faster than exponentially. So these are unbounded measures. This mu t and mu h, they are unbounded measures because the moments go fast. But also you have a control on the tail, because if you have an upper bound on the how fast the moments are going, you have. But what moments don't tell you, or easily, so is the measure, is there density? So you have the moments of a probability measure. Does it have a density? Is it smooth? Is the density smooth? If it exists. Is it unimodal or bimodal or any such thing? These things are not apparent from the moments of a measure. Okay? Actually, so it's a very interesting problem. If given a sequence of moments, a very famous classical problem in analysis is given a sequence of numbers, is it the sequence of moments of a probability, unique probability measure? It's the famous moment problem, which has a very clean solution. There is another one which is not as well known. Given a sequence of numbers, is it the sequence of moments of a probability measure on an interval with a bounded density? This question, it's usually never taught in any course, maybe because it's maybe too complicated, and maybe because it was completely solved by Markov a very long time ago, actually. There is a very specific answer, but it is too complicated to employ in these situations. At least I don't see any way of using those criteria. There are many inequalities one has to check that this happens, and that I don't see any way of doing it when these are not explicit. Actually, the best way, there is only one previous example, or there are a few previous examples in random matrix theory where the limiting measures were known. For example, the well-known Wigner matrix, in which you have all entries IID on the upper part of the matrix. In that case, the same method was used by Wigner. That was the starting point of use of method of moments in random matrix theory. There it turned out alpha p was very explicit. It was just the Catalan number. And then one knew or could guess that these are the moments of this particular measure, and so you had the density. Otherwise, you would not know that this Wigner semicircle law was what was behind. There you had explicit formula, but here we don't, and that's the challenge. So, but well, okay, mu t is misleadingly like the Gaussian. Our proof sort of explains it but doesn't prove it. Actually, the first 6 moments are the same as that of Gaussian. It is the 8th moment where they change. I mean, that you can see from the moment formulas here. Yeah, so, well, what we do gives various indications, but what we have extracted is less. I'll tell what we have, So as to these questions are still, we don't know. Okay. Yes. Yeah, I will. So these questions, we have nothing so far, although there are some indications in our method of proof. For this, Arnab Sen and Balint Vivek showed that the answer is yes for Toeplitz case. That is, mu t has a bounded density. No, it's a deterministic measure. It's a non-random measure. Yeah, mu t. We are interested in what is the limiting measure.
The mu t is not random.
It's not random. It is a measure which has a bounded density. That they showed. And our theorem is that we prove the same. I mean, our proof also gives a slightly simpler proof for their theorem. So we show that both mu t and mu h have bounded densities.
They're not stochastic either.
No, that was already known. I have written there. It's not random.
Not random.
Yeah, that was already known. So they have bounded densities. That is the point. And the bound we get is actually pretty good. It is about double what it should be, it looks like. Whereas their bound was something like 16, 17 times higher. It's not something we were aiming for. Our method of proof gives that. Okay. So now, let me see. Yeah, how do you get to the density? That's the question. So what I want to do in the rest of the talk is give an indication of the proof of this theorem that these have bounded densities. Okay, so No, I would like to address, but I don't have the results.
You don't have the results.
Yeah. No, we don't have. Yeah. So otherwise I would advertise it well. So, so mu t and mu h have density, bounded density is all we have. That too, the proof I'll mostly give for the Toeplitz case, and maybe indicate there is extra bit for the Hankel case. Now, what is the way to do? Here, your question is sort of relevant. See, what conditions do we have which assert the existence of density of a measure? So you may have seen some things in analysis. There is a famous theorem of F and M Rees, but maybe more basic, yeah. So if you take the Fourier transform of a measure, the characteristic function of a measure, probability measure, and it is absolutely integrable, then by the Fourier inversion formula, we know that there is a density, and the density is bounded by the L1 norm of the Fourier transform, right? So that is one example. So that's exactly the way we will go, but not Fourier transform. That is not so suitable in random matrix theory, but there is a different integral transform, like the Fourier transform, which we will use. This is also what Sen and Vivek use. This is what is called the Stieltjes transform. Okay, so first I will give the basic thing that we have to prove, and then tell what we have done. So the main gadget is Some people call it Borel transform, and maybe there are many others who call it other things, I don't know. What is it? If mu is a probability measure on R, then the Stieltjes transform is defined as the integral of 1 over z minus x d mu of x. Okay. So this is well defined for if z is on the line, then we don't know, but if z is in the complex plane, then it is well defined. Anyway, it's complex, so it's symmetric, there is a conjugacy, so we may just take imaginary z positive. So on the upper half plane, it defines a very nice complex analytic function, and this is the integral transform that is used in random matrix theory. Now, there are two things. Why is it useful in random matrix theory, and what are its properties? What is, like the Fourier transform situation, how do we get the density and stuff from here? Okay, so some basic facts. G mu okay, that's the first thing. G mu determines mu. Okay. So in some sense, the way to think of all these, I mean, the Fourier transform or the Stieltjes transform is, at least in nice enough situations, you can expand it in powers of x, and then it's what it is it has all the information of all the moments together at once. But this is well defined even if mu has no moments, like with Fourier transform. Okay. So G mu always determines mu, but here is the actually the why is that the case? In fact, what it is if you look at imaginary G mu of, let's say, x plus Iy, so you look at it somewhere in the upper half plane, here is x plus Iy. What is imaginary G mu of x plus Iy? If you divide, okay, so there is a, okay, if you do minus 1 over pi of that, it is actually the density of mu convolved with the Cauchy measure with the parameter y. What is this? This is the one with density y over pi into 1 plus y square. See, this is a Cauchy density scaled up. So what happens is, so this is clearly the Stieltjes transform has the information about mu convolved with the Cauchy density. Now, as y goes to 0, this Cauchy density becomes narrower and narrower, and mu star Cy just converges to mu. Therefore, you have the information about the measure from this. Okay, so that's how you get it. From that also it follows the following, that if so the density of mu at x is just the limit as y goes down to 0 of minus 1 over pi, this imaginary G mu of x plus Iy. Okay. It means in all ways. So if this limit exists, then the mu has a density at that point, and conversely also, if mu has a density at a point x on the real line, then this limit will exist, and that they are equal. So because you just see that as y goes to 0, this converges to mu. So if you do a little bit of work, the densities will converge to the corresponding density. So this is the density of that, so that will converge to the density of mu itself. So this is the basic fact about Stieltjes transform which we are going to use. And what is, so hence what we all that we need to show is, so if you want to show that the mu has a bounded density, it's enough to show that, so to show mu has bounded density, it suffices to show the imaginary part of G mu is bounded in the upper half plane. In the upper half plane means imaginary z positive. Okay, so if you do that, then you get the density. Okay. Huh? Here, this. No. I mean, no. Well, it's that's fine. This is true. I have not said, I mean, I don't want to go over the tutorial on Stieltjes transform, but yes. No, this will be fine. If you show that the imaginary G mu is bounded, then it is fine. Actually, yeah. No, there we know that they are non-random. Yeah, maybe law of large numbers or Byc-Dembo-Jiang paper, anything tells us. Yeah. No, that has nothing to do with. So, for a measure to have bounded density, it suffices us to show that the Stieltjes transform, or even just the imaginary part of it, is bounded on the upper half plane.
That also will imply that the limit
Yes.
exists.
Actually, okay. Yeah. So, well, if you want to know the measure of AB, instead of talking about densities, if you integrate this g mu of x plus imaginary on this A to B, you will get the measure of this. So if you show that this is bounded by some constant, this will be bounded by constant times the length. And that limit will be mu of this. So you will get that mu of any interval will be bounded by a constant times the length of the interval. That implies that it has bounded density. No. So in random matrix theory, this is useful for the simple reason that when we talk about Ln bar, so when we talk about Ln, say Ln bar, what is G Ln bar? G Ln bar of Z is nothing but 1 over n expected trace of Zi minus Tn inverse. Let's say if we are talking about the Toeplitz random matrix. That is the reason why we may have a handle on this. So what we need to show is that these quantities are bounded uniformly over Z and n. Okay, so this is the reduction. I will not write it again. So in case of both Toeplitz and Hankel, because of these facts about Stieltjes transform, all that we need to show is that this quantity 1 over n expected trace of Zi minus or matrix inverse, this quantity, say absolute value of this, is bounded uniformly over Z in the upper half plane and over n. Okay, so that is all we need to show. Maybe I'll just write it here. Sorry. Yeah, this is Tn over square root n, which is what I would like to consider. So G Ln bar of Z is less than equal to C, uniformly over n. If you show this, then you get everything.
This was the approach of Sen and Vida.
Yeah, so that is the same.
And they also had some special way of writing the Toeplitz.
Yeah, but our way is, in my opinion, simpler. And this is actually, I think it is very important maybe, but well, okay, you'll see. So there are two steps in the proof. So I want to explain how we get to that. Okay, so in both the Toeplitz and Hankel case, there is similarity. There are two similar steps. In the Hankel, it is a little more complicated, the second step. But the first step is very similar, and it is a very interesting idea. So, well, it's my collaborators. So, yes. No, I think it's a really interesting idea. I have not seen this before. It may be of use even in just study of Toeplitz matrices in general. Maybe it is known, but I have not found it so far.
The excuse have the Gaussian distributed.
Well, okay, a good question. I didn't say this. In the Byc-Dembo-Jiang paper, they assume that xi's they allow much wider class of distributions.
Oh, they do.
Yeah. So, but since our answer is about the limit, our proof works with the Gaussian case. We use the Gaussianity, but they don't need it. But the limit is the same. So the conclusion is about the limiting distribution.
So even the heavy tail case.
Huh?
Even the heavy tail case like a
No. I said there are conditions, of course. Yeah. Assume that they have all the moments, then it's okay. Second moment. Okay. So what is first main idea? In both the Toeplitz and Hankel case, the idea is the following. So let me write the facts and then explain how. So we can write Tn as a sum of two matrices. First I'll say what it is we do and then explain how. So we can write it as two matrices where An and Bn are independent random matrices. First of all, they are independent matrices of each other. Eigenvalues of An are, let me say, almost IID normal 0, 1. It's explicit. An can be explicitly diagonalized and its eigenvalues are almost IID normal 0, 1. I'll explain the almost later. And exactly the same is true of Bn. Okay. So, and a similar thing is true for the Hankel case. In Hankel case also we can write it as a sum of two matrices. And again An and Bn are independent. What is different is that the eigenvalues of or Bn are not normal, are almost IID with Rayleigh distribution. Well, symmetrized Rayleigh distribution. I mean mod x e power minus x square by 2, that's the density. Okay. So if you see how that looks, so normal distribution, of course, everyone knows how that looks. The Rayleigh distribution looks like this. Okay. So now if you see, you expect, see, two independent random matrices are being added. We understand individually the spectral distributions are Gaussian and this. So this should be, the spectral distribution of this is some kind of a convolution of this normal with itself, some kind of a convolution of this with itself. That sort of explains the picture, but we don't understand this convolution that well, so we don't have all the things. Okay, but this convolution is neither the usual convolution nor the free convolution that comes in free probability theory. It is some different convolution, very complicated. I know it in terms of moments, but not in terms of transforms. So I don't know what it is. But that is sort of explaining why we see this picture. Okay, the unimodal and bimodal, if you for the IID, for the independence, I'll tell you what it is. So how do we get this? Okay, so let me explain. This is the nice idea. See, everything about, let me explain, stick to the Toeplitz case and explain. What is the Toeplitz matrix? Everything under the Toeplitz matrix is in this, we can write Toeplitz matrices in terms of this one matrix, right? So what is Tn? Tn is nothing but x0 times identity plus x1 times L plus L star plus x2 times L square plus L star square. If you do L square, you will get once on the next diagonal, L cube will be once on the next diagonal and so on. Okay, so this matrix L is the key thing. So it is very tempting and has been done many times that L is almost looks like you put a 1 here in the n comma 1 entry. Okay, so everything else is, it looks almost like that, just one extra 1 if you are willing to give, we can put that. This is a circulant matrix which is very nice. But the courageous step here is to not be wishy about it, but write it as and a -1 here. Okay, so that will give us 2 times L.
So L is a probabilistic matrix.
Yes, this is.
But then the Tn is random because of the.
Well, for now, the randomness is not important. It doesn't matter. Anyway, let's write it like this. So this matrix is C, this matrix is D. Okay, C and D are both very nice matrices. What are they? C and D are both unitary. So this is circulant. This we can call twisted circulant. If at the end there is a twist. Okay, I don't know if it has a name. This is a very nice matrix. Okay, the point is they can be diagonalized. They are very nice matrices. We can diagonalize them explicitly and so on. But what happens then, but not only is L like this, if you do L square will have ones up here. So L square will be C square plus D square. So in fact, 2 times L to the power P will be C to the power P plus D to the power P. If you raise it to a power P, at least for P less than equal to N minus 1. Okay? And also 2 times L star to the power P is C to the minus P plus D to the minus P. L star is, because C star is C inverse, C and D are unitary. So the point is, because of this, we can write this entire matrix in terms of C and D. So what this leads to is, if you write this L and L stars and powers of L and L star in terms of C and D, you just get a polynomial in C and a polynomial in D, a sum of the two things. So you get something like AK C to the power K, okay, plus some BK D to the power K, where
AK and BK are going to be random.
They depend on X, yes. K, okay, for strictly speaking, here let me take N to be an odd number, that otherwise I had to write other complicated forms. So I'll write minus M plus 1 through M minus 1. The fact is C to the power N is identity and D to the power N is minus identity. So if N is 2M minus 1, all the powers higher than M, you can bring it to powers, positive and negative powers between minus M plus 1 to M minus 1, that's all. So point is that any Toeplitz matrix can be written as a sum of two matrices. One is a polynomial of C, one is a polynomial of D. And you know, these are completely diagonalizable. They are in the algebra of C, this is in the algebra of D. We know its eigenvectors are not changing, eigenvalues only are changing. What are the eigenvalues of this? Well, there will be sum of, with Gaussian linear combinations. So now you see that they are all Gaussians, except you have to calculate the correlations. They are very small. I'm not going to write down exactly how small. This is how we get this fact. Since in interest of time, let me move to the step 2. This is the step 1. And for Hankel, it is very similar. So we can write it as a sum of two matrices. One is a polynomial of C, one is a polynomial of D. Okay, sorry, very good. What is AK? In this case, AK will just turn out to be xk plus xn minus k over 2, and bk will be xk minus xn minus k over 2. So they are completely independent actually. Here I use the Gaussian assumption. Okay, so if you just follow it.
N is odd in this.
Yeah.
But then you consider the even case as.
No, we know the limit exists, we don't have to.
Okay.
So you can consider, you can write slightly different forms for the even case, but it's not important. So this is how we get this independent random matrices. This is nothing to do with randomness. In the end, you can put in randomness if you like. Then we get independence when you put Gaussians. But otherwise, this is... So one of the things, what I meant by it may be useful in also in Toeplitz matrices, one of the famous theorems about Toeplitz matrices is the Zero limit theorem, which talks about determinants of going Toeplitz matrices. Actually, one can check, because these are explicitly diagonalizable, Zero limit theorem is explicitly valid for both these individual components. I don't know how to deduce the Toeplitz from that, because determinant of the sum and sum of, is not clear. Yeah, it's very similar, but what there is a twist, but I will not get to that. What happens is that in the Hankel case, you do not, you get this an and bn. Now I said it is best to not, the point here is that all Toeplitz matrix, this thing, only the eigenvalues change. Eigenvectors are the same for whatever x case we put, right? Because this is a polynomial of C. In the Hankel case, it is not quite like that. It is best to reduce it to it. If you reduce all the way to the eigenvector level, then there will be dependence on the A case, on the X case. But you have to, it reduces to some 2 by 2 blocks. Okay, I don't want to, since I have only a few minutes, let me not go there. Let me explain the Toeplitz case, the second part. True, but yeah, so when you go to all the way to the end, there is a dependence. So, but whereas if you can reduce it to a sum of these 2 by 2, you can find, here you find these, eigenvectors means invariant subspaces of dimension 1, which you have found. There you find invariant subspaces of dimension 2, which are deterministic, not depending on the entries. That's the point. So the second part is called spectral averaging. So this is a known technique. Again, what is actually new is in the Hankel situation. The Toeplitz case is known, but again, for the lecture, I'll just explain the Toeplitz case. So what is that spectral averaging technique? So here is a lemma, let me just say. First, let's go back to what it is that we want. We want to understand the 1 over n expectation trace of Zi minus Tn inverse. Right? So this is the quantity we are interested in. Now, the trace can be evaluated in any kind of any basis. So what we can, so you write, I was a bit loose in what I said there when ANs are independent. So let me write, what turns out is that so this is it's not that all the n eigenvalues are independent. There is one eigenvalue, lambda naught, with a one-dimensional eigenspace, and the rest of the eigenvalues come with a two-dimensional eigenspace. So I have written it as a sum of projections with those things. These are rank 2 projections, this is a rank 1 projection. So we can expand this in that basis of this projection. So this is the same as k equals 0 up to m minus 1 trace of P Zi minus Tn inverse P. You can sum it and then take expectation. Or you can put expectation here. It's the same because sum of the projections is identity. That gives the full eigenbasis of this one. Okay. So we have to evaluate these kind of things. So expected trace of P Zi minus Tn inverse P, where P is a fixed projection matrix that's not random. So that is the spectral averaging technique. See, you just have to show each of these is uniformly bounded. I want to show this is, for this I want to get a bound which is independent of n and z. So it is enough that I get a bound for the kth term which is independent of n and z, then the same will hold because I'm averaging the m minus 1 of them. M is about half of n, so it's the same. So how do we get a bound on this? So this is the general fact. So if you think about it, here P, I didn't write, this is Pk. Sorry, this is the kth projection. So when you're talking about the kth projection, there is one random variable. You condition on everything else. So you can write Tn as lambda k pk plus something, this is fixed. You can condition on the rest and work with it. Since I'm assuming like lambda k's are independent, let's say. Then you can condition on them and work with this. So the general form is, I have some matrix M, let's say n cross n symmetric matrix, and P is a d-dimensional projection, say rank 2 projection. rank D projection, and you form M lambda, which is M plus lambda P. That is how this looks. If you fix this, then there is one parameter, namely lambda K, and it is that parameter perturbed by this lambda. The statement is that if I look at the trace of Zi minus M lambda inverse, P times Zi minus M lambda inverse P, and then the idea is this, that this lambda we know is Gaussian, right? So if this is absolutely continuous, it would be very strange after doing everything you get something that's not absolutely continuous. So that's the averaging thing that we have to do. So if I integrate this with respect to, let's say, the Gaussian density or something like that. So if I condition on the rest, then I average over just that lambda K variable, then I get a quantity like this. The claim is this is bounded by pi times the sup norm of phi. This is the spectral averaging lemma. Okay. So once you apply this, this is immediate. Then when you fix this, apply this lemma, you condition on all the variables, the B matrix as well as all the lambda j's other than the kth one, and then you do this expectation first over lambda k and then over the, so when you do expectation over lambda k, you get an integral like this, which is bounded by this. And then you are averaging that n times, so you will just get a bound. So that's the point. Okay, so it's not time to show the proof of this lemma. So let me just, can I take a minute? So I'll just tell some things that in the Hankel case, the spectral averaging lemma is much more complicated. We don't have projections. That is what makes it difficult. So, but and the integral is over the complex plane. There is some non-trivial point there. Okay. I just want to say what else is there. So as some of them I have already mentioned, we don't know the smoothness of the density. So far we have not been able to do the smoothness of the density, or the unimodality or the bimodality of the Toeplitz and Hankel cases. What else one can do is one can go to more general groups. G is a countable group, suppose. Then a Toeplitz matrix is something that looks like this. The G comma H entry depends only on G inverse H. And a Hankel matrix is one whose G comma H entry depends only on G times H. So if you take the group to be Z, then you get the usual Toeplitz and Hankel structures, constant on this diagonals or on these diagonals. So one can ask in a general group whether we can put IID Gaussian and do the same. And what we are able to do so far is, in the case of ZD, our techniques work, but in general, I don't know what one can say. Okay, thank you.